Hello, this is Nicholas. I found a really cool problem that I wanted to share with you all. It was actually on, if you guys are familiar with it, it's on the site brilliant.org, under Contest Math Level 2. So the problem was, they gave you the function, the floor of 1 over x to the negative 1, or in other words, reciprocated. And maybe kind of as a note on the side, the floor of x, if you all aren't familiar with that, is the greatest integer, and that's important, integer less than or equal to x. So, for example, the floor, say 2.8, is 2, or the floor of negative 2.8 is negative 3. Okay, now, what do we want? The area below this curve and above the x-axis for for 0 being less than or equal to x being less than or equal to 1. So, and also you can, now I'm sure, for those of you that know calculus, you're probably thinking to use integrals, but you can do it without calculus, which is the way I'm going to show you all. So first of all, I think what might be of good help is to look at a graph of this here. So, here I got lovely graphing utility, Desmos. And so along here is the area we're looking at. Now, you can see the, let me get my marker out. Sure. You've got like kind of rectangles, like, oops, it's a little wavy at the end there, but like, that's a rectangle, and then, like here, and here, and there, and there, and there. You see, they're all rectangles, and they're getting infinitely smaller as we go down to 0, and it turns out that there's an infinite amount of them. But in other words, if we were to find the area of this rectangle, this rectangle, this rectangle, this rectangle, all these infinite rectangles, and add up their areas, then we would get the area under this curve from 0 to 1. So, no. So, let's see here. Let's just use first, because that's the first thing that I would think to do. Let's say let x be equal to 1/2. Just kind of spitballing here, I guess. So we get the floor of 1 over 1/2. There shouldn't be a bracket on the top, just on the bottom. To the negative 1, which is the floor of 2. I keep doing that bracket on the top. To the negative 1, which is 1/2, because the floor of 2 is 2, to the negative 1 is 1/2. So we get 1/2 there. Now, let's say we let something be just a skosh over 1/2. In other words, like 1/2 plus maybe 0.0001 or something like that. Now, we're gonna get, what are we gonna get? We're gonna be dividing by a slightly bigger number, right? Like, maybe is the graph still pulled up? Oh, dang, it's not. See, let's see, how would I say this? Like, if we've got 0. Let's say 0.51, okay? And we do 1 divided by 0.51. Since that's a slightly bigger number, right? What? What was I doing? Let me plug in the graph again. Sorry. We should be getting a bar from 0.5 to 1. So floor 1. I didn't realize me drawing with the rectangles would get rid of it. It's kind of annoying. Okay. Right, okay. So 0.5. Now, yeah, okay. So we plug in 0.51. We're going to be dividing by a slightly bigger number here, which means we're going to get a slightly smaller number here. We're going to get a number just a little bit less than 2. It turns out to be approximately 1.96 here. But so in other words, when you take the floor of 1.96, you get 1, and 1 raised to the negative 1 is still 1. So, and if we plug in any number between 1/2, exclusive of 1/2, because we get a half when we plug in a half, but inclusive to 1, because that's where our interval ends, when we evaluate that function, we get 1. Okay? So, now, if the pattern isn't... Let's do one more. So, let's let x be like a third. Okay? So we get the floor of 1 over a third. Hey, I didn't do the bracket on the side. To the negative 1, which is 3 to the negative 1, which is a third. So, now if we plug in something just a little bit bigger than a third, like x is equal to, maybe 0.34, because a third is 0.3 repeating. We're going to be dividing by a slightly bigger number here. So, okay, well, what I did in my head here was 1 over a third is the floor of 3, the negative 1. So we're going to be getting, when we divide by a slightly bigger number here, we're going to get a slightly smaller number here, a number less than 3. So when we take the floor of, negative 1. Why did I write a negative 3? Negative 1. So when we take the floor of that number, we're going to be getting 2, since it's just slightly less than 3. And when we raise that to the negative 1, we get a half. So, in other words, from the interval 1/3, not including a third, to a half, including a half, when we take this function, we get 0.5, or a half. So, now, as you saw from the graph, and as I told you, there are an infinite amount of rectangles here, right? So rectangle, as I drew them, there's an infinite amount of rectangles, so we can't just, we have to think in generalities here, and then maybe use summation to get an answer, an infinite summation, since there's an infinite amount of rectangles. So I'm gonna make this statement here, and if you don't, agree with it or it doesn't make sense, you just kind of have to meditate on it some. So my claim is that on the interval of 1 over n plus 1 to 1 over n, the function is constant. Right? And we saw that. You know, I used my inclusive and exclusive stuff to make things a little bit more specific, but anywhere along this interval, the function's constant. So basically, we can sum up all those different rectangles along the nth interval from 1 to infinity, and we're gonna get an answer. So now the area of the rectangle is the length times the width, and the length is really f of x. In other words, how tall the rectangle is, your y value, and the width is really just your x value. In other words, how far you had to go from the nth subinterval to the nth plus 1 subinterval. So let's see here. Now on this interval here that I just wrote really big, your height, f of x, is going to be 1 over n, because yeah, like how I worked through it, like here and here, and if that doesn't make sense, just think about it some. And now your width, your width is what? It's well, it's, you know, the distance between two x values, 1 over n minus 1 over n plus 1, right? This x sub 2 minus this x sub 1. And when we put these over one denominator, we're going to get n plus 1 minus n over n times n plus 1, otherwise known as 1 over n times n plus 1. Now, our area then, so our width, our height is 1 over n, and our width is 1 over n times n plus 1. So our area turns out to be sigma n equals 1 to infinity, since there's an infinite amount of subintervals, an infinite amount of rectangles, of 1 over n squared times n plus 1. You know, this value here times that value there. Now, I can kind of look at this, and I know that this sum is going to telescope, so I'm going to use partial fractions on the argument here. So 1 over n squared times n plus 1 is equal to 1 over n plus, why 1? Oh, because I was thinking ahead. A over n plus b over n squared plus c over n plus 1, where a, b, and c are the constants that we want to find. Now I can actually, I'm going to take the shortcut lazy way, because laziness is always a good idea in math. So I'm going to use what's called the cover-up method, and it's kind of a little hard to illustrate on this little whiteboard or whatever you want to call it here. Whoa. But basically what you do is okay, like I'm gonna find this b first. So basically what you do to find the b is you're gonna cover up this n squared. You know, maybe you're writing on a piece of paper, you're gonna cover up that n squared with your hand. So you're just looking at 1 over n plus 1, okay? You pretend you just have 1 over n plus 1 for now. The n squared is just gone, okay? And then you say to yourself, what makes n squared, what value of n makes n squared 0? Well, it's 0, right? So you plug 0 into here to get 1. 1 over 0 plus 1 is 1. So b turns out to be 1. And why that works, I mean, I don't want to get all into it right now. I could make a separate video on that if you all would be interested. Basically, it has to deal with the fact that you kind of have these removable discontinuities, and you can plug values into those and get an answer. So now I'm going to do the same for the C here. I'm going to find C using the cover-up method. Now I'm going to cover up this n plus 1, so I just have 1 over n squared. You know, that n plus 1 is gone. Now I'm going to say to myself, what value of n makes n plus 1 equal to 0? Well, that would be n is equal to negative 1. So I'm going to plug negative 1 into here to get a value of 1, because negative 1 squared is 1 and 1 over 1 is 1. So that means C is equal to 1. Now I can't use this cover-up method to find A because I have an n squared in the denominator. I don't have an n. And you have to build up, you have to build up the powers when you're doing your partial fraction decomposition. So, but what you can do is, I know everything except for A, so I can just pick a value for n that is nice and then find A. So I'm gonna let n be equal to 1, so I get 1 over 1 squared, I'm getting it from here, 1 squared is 1, times 1 plus 1, that's a half, is equal to A over 1, or A, plus 1 plus a half, from plugging it in now onto this side. I'm going to subtract a half from both sides, so that goes away. And I'm going to get that A plus 1 is equal to 0, or A is equal to negative 1. So this original sum becomes sigma n is equal from 1 to infinity of, I'm going to write it like this, 1 over n squared plus 1 over n plus 1 minus 1 over n. Now I can evaluate each one of these summations separately, but I'm actually not going to do that. I'm going to evaluate this first one separately because it's a very famous sum that I introduced in one of my other videos, and then I'm going to evaluate this sum together because it is a telescoping sum, and it's pretty clear that is the case because you're subtracting, and so a nice bunch of things are going to cancel out. Now I'm going to write this on a new page. Okay, let me just make sure. So sigma n equals 1 to infinity, 1 over n squared, plus sigma n equals 1 to infinity of 1 over n plus 1 minus 1 over n. Now, this is a very cool sum, and the answer to this sum is called the Basel problem, actually, not the Basel problem. We're not going fishing. And it turns out to be pi squared over 6. That sum. Yeah, that will probably take a whole video and then some in on itself to prove, but believe me, it is pi squared over 6. Now, this sum here, I'm going to write out the first few terms just so you all can get an idea. Letting n be 1, we get a half minus 1 over 1 plus a third minus 1 over 2 plus a fourth minus 1 over 3 plus a fifth minus 1 over 4 plus dot 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 plus 1 over n minus 1 over n minus 1 n minus 1 plus 1 over n plus 1 minus 1 over n plus dot dot dot. This goes away, goes away, goes away, goes away, goes away, goes away. There's really a 5 there, that'll go away. Go away, go away, go away, go away. Go away, go away. Oh. 1 over... Oh, that's an n minus 1. Whoopsies, I shouldn't have had that go away. I guess I should... I'm going to erase that. Try to be careful. Okay. Plus, we had plus 1... Oh, this is the nth term here. those are all going to go away, and now we have this nth term here. So we ended up getting negative 1 plus 1 over n plus 1 minus 1 over n plus dot dot dot. Now this is going towards infinity, so basically we have the limit as n increases without bounds of this, which is, and because we're letting n get bigger and bigger and bigger here, which is negative 1 plus 0 plus 0, or negative 1. So pi squared over 6 minus 1 is the area we are looking for. I think that's such a cool problem. I did kind of want to touch on it. Just kind of give an outline. This is Euler's way of proving the Basel problem. I don't know, whatever it's called. Now, you need to know calculus for how Euler did it. And this is really just the end of his proof. You know, how he got all this stuff is in his paper, if you are so inclined to read that. But basically, he starts, well, he doesn't start, he ends, he starts the end with the infinite Taylor series expansion centered at x equals 0 for sine of x. That turns out to be equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot dot dot. And if you know any calculus, this should be very familiar to you. Now, the zeros of sine of x, just normal, you know, considering left side, are 0, you know, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, yada yada yada. So Euler made the leap basically in claiming that the polynomial on the right side can be factored through its zeros that we've given here for the one on the left side. So he basically claims that this is going to be equal to x, because you get the 0 here. What makes x 0? Well, x equals 0. Times 1 minus x over pi times 1 plus x over pi times 1 minus x over 2 pi times 1 plus x over 2 pi times 1 minus x over 3 pi times 1 minus plus x over 3 pi dot dot dot, and then you'd have a times 1 minus x over 4 pi, yada yada yada. And since both sides are zeros at the same places, we can divide both sides by x. And so of this whole big equation here, we're going to divide both sides by x. So we're going to get 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial. And that's equal to 1 minus x squared over pi squared times 1 minus x to the okay, so I'm using the difference of squares here, dude. X squared over 4 pi squared times 1 minus x squared over 9 pi squared dot dot dot. I use the difference of squares. See here, 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 and so on and so forth. Now the constant terms of both sides agree. They're both 1. So, this kind of crazy procedure might be valid. So, we're gonna basically, some algebra happens, and we're gonna set the, let me make sure right, set the x squared coefficients equal. So we get negative a sixth is equal to negative 1 over pi squared minus 1 over 4 pi squared minus 1 over 9 pi squared minus dot dot dot. And so multiply both sides by negative pi squared, and you get pi squared over 6 is equal to 1 or 1 squared plus 2 squared or 4 plus 3 squared or 9 plus 4 squared or 16 plus dot dot dot. A QED. I wouldn't really consider that a full proof though. That was a very, very basic outline, but that's kind of the idea there of what's going on. I just thought that was such a cool problem. I wanted to share it. If you have any questions about that problem, I would love to answer them. I think for now, we're done.